Okay, so we have discussed the, some formalism of quantum mechanics, right? Like how to denote a state. Right, so we said that the state in quantum mechanics is a possibility. Is a ray, actually a non-zero ray in the Hilbert space, right? So we have different ways to write down this one. So we can say use a wave function, say for example per psi x. But we can also use a Dirac rotation, say per psi, right? And then we can also use a matrix, C1, C2. Okay, so we can denote this as just per psi. Okay, so it's a column matrix. So this one has one column. Okay, and then you can also have the compass conjugate, right? And then in the Dirac rotation, we write down this as this one. So this one actually can be understood as an Hermitian conjugate. Because if you look at the matrix, it will have be this form. So this one can be written as per psi DAG, right? So that's basically you take the transpose and then take the compass conjugate, right? So that is the notation in the matrix. You can also have a basis. You can have a per psi 1, per psi 2, a basis, right? Or you can also use this one in Dirac rotation, okay? So you have a basis, okay? And this one, then you can, in this notation, the basis is something like this one. So this is the first one. The second one is just like this one. Okay, and then the third one is something like this one. Okay, you can have different of this one. Okay, so of course you can call this one per psi 1, and this one per psi 2, and this one per psi 3, right? Just three different column matrices. Okay. You can have inner products. Okay. For example, if it's one-dimensional wave functions, you have something like this one. And then in this Dirac rotation, we write this one in this form, okay? In the matrix form, we say that you have a column matrix. You take the Hermitian conjugate times 5, and this one, of course, can be written as C1, C2 compass conjugate, and then times say D1, D2. Right. So this one is a 1 times 1 matrix. Right. That's a compass number. Okay. And for the basis, you have also normal condition, right? So that means you have per psi m x, per psi m x. You do the integration, so that equals to delta m and m. So in the Dirac rotation, let's just say that the m and m is the delta m and m, right? Or in this one, that's even simpler, right? So you can say it's obviously per psi m DAG and per psi m that equals to delta m and m. Oh yes, so this one is you're right. Sorry, there's a typo right here. Thank you. That's the DAG of this one. So this is also normal, right? You will also have a completeness. So that means any state, any function satisfy the same physical conditions can be written as the summation, of the basis, right? Okay. This coefficient, of course, can be just written as this inner product between the basic state and the wave function that you want to expand. Okay. And correspondingly, you have the Dirac rotation. So any precise states can be written as a summation of m, cm, and m. Okay. With this coefficient, it's just the inner product between the basic state m and the state that you have. In the matrix form, so any matrix can be written as a summation of m and this unit of vectors, right? Okay, that's obvious. And with this Cm, it's nothing but just the inner product, the matrix product between these basic states, image conjugate, and the state and the one that you have, right? Okay. And also you know that physically, the state per set x is the same as any complex number times per set. Okay. And similarly, a physical state is the same as this one. So if we multiply a constant to this one, actually it does not change the state. Okay. And also, this is the same, right? Okay. So let me make this one to be smaller so that you can see this in one page. Okay. Right. So this is the Dirac rotation and the matrix representation of the state. So this is the state conjugate basis, right, and the inner product. Okay. Let me say a few words about this inner product, the physical meaning of this inner product. Okay, like this one. So the physical meaning. So this one is just basically, it's the probability amplitude of finding the possibility aside. Okay. Given the state. Right. So let's say, in classically, you say if you have one possibility, and you can say that if you have this possibility, so this is basically the conditional possibility, right? Probability amplitude. So if you have one possibility, and then you ask the question, given this possibility, what would be the possibility to find another one, right? So in this sense, this is just the conditional, the probability amplitude, because in quantum mechanics, we not only have a probability, we have a probability and amplitude, right? So that's the physical meaning of this this term, okay? Right. And another physical meaning of that this is also orthogonal, and then immediately, if you have two states equal to 0, so that means they're mutually exclusive. Okay. So that if you have this possibility, and then you can have another one, and vice versa, right? Okay. So that's the summary of the state. Okay. Okay. And we also know a little bit an operator, right? So if you have an operator, we actually consider the linear operator, okay? Right. So then you have if you have a wave function per psi x, you apply an operator on this one, you actually got a new state. Let's call it per psi prime. You can also use the Dirac rotation, right? So in the Dirac rotation, you can apply the operator and per psi. You got of course a new state per psi prime. And you can also have a matrix, of course. If you have a column matrix, so this one, remember, is n times 1 matrix. So if you have m times m matrix multiplied to this matrix, you got a new matrix. And this one will be, is also m times 1 matrix, right? Okay, so that's the 3 different ways of writing a linear operator in quantum mechanics. You can use either the one that we are familiar with, apply this one to a wave function, okay? Or you can just use direct rotation, okay? And since it's linear, so you can act on a basis, states. So this is particularly interesting. Right, so this is the basis state, and this one, of course, will give you a new state. Right. And similarly, in the direct rotation, you got a new state. Okay. And in matrix, of course, you also have this one. Sorry. So you have a matrix, n times n matrix, acting on the nth basis column matrix equals to the new one, right? Okay. All right. But remember, this percent m prime x can be always written as some coefficients. Let's say can be always written as, again, some coefficients, right? And what will be this coefficient? And this coefficient, according to what we have learned before, should equals to the summation percent m, the integration of percent m complex conjugate and percent m prime complex conjugate, right? dx. So this one is nothing but just so let me call this m, sorry. I always made this kind of right. So this is again nothing but just the matrix element. Okay. So if we summarize this one, so basically you find that the percent m, the A acting on a basis state will give you the summation of m, and then percent mx and a m m. Right. So that is the result that we have for for a basis state. Okay. And then similarly, so you have A acting on this one, right? So this m prime, of course, can be also written as a superposition of the basis state, right? And this coefficient again will equal to m and m prime, right? Sorry, this m prime should be right here, okay? Okay, right? But this new state is nothing but just A acting on this m, right? So this is nothing but just the matrix elements, of course, right? So that means, again, you have this one. Okay, that's very interesting, right? And now let's look at this state, this matrix form. That's even simpler, okay? What is the percent m? Okay, percent 1 actually equals to 1, 0, 0. Right, percent 2 equals to 0, 1, 0, and so on and so forth, right? Okay. So what is this A matrix then? The first of all, A percent 1, for example, that equals to, let me write this A11, A12, A matrix, A21, A22. Right, this is the matrix. Times, for example, 1, 0, right? That's the percent 1. By linear algebra, you know that this one is nothing but just the first column of the A matrix. Okay. And of course, you can look at the times percent 2, that will be also this one. A11, A21, A12, A22, right? But now it's 0, 1, 0. And this one will give you the second column. That's A12, A22, A32, and so forth, right? So you can see that that basically A times percent M, that's A11, A12, A21, A22, so on and so forth, times and 0, 1, 0, okay? Just give you the nth column of the matrix A, right? Okay, so this immediately means that the percent M prime just equals to the A M1, A M2, so on and so forth. Okay, right. But remember, this can also be written as a summation of, if you want, MCM and the percent M, right? And with the CM equals to the coefficients, that's CM. CM equals to percent M DAC and percent M. Okay, so this is nothing but just A M M. So now you can compare all of this one actually consistent, right? Okay. So what does this mean? That means the matrix form. So all of this will give us a matrix representation. Okay. So we can have the matrix A is nothing but just, you know, with a matrix element. Or in wave function form, that's a percent M. Okay. Right. So this is what we have obtained for the matrix representation. Okay. Right. So for any linear operator A, you can have you know, a Dirac rotation like this one, and then you can have a matrix form. Okay. So this is a matrix form with the definition of the matrix elements, just given by this one. Okay. And then you can say that for any state, if you have a state, for example, if you have a state percent equals to summation of M Cm percent Mx. Okay. And now let's look at what's the transition of this one. That's so the transformation of this state will just equal to summation of M Cm A acting on percent Mx, right? Remember, this is a linear operator, so you can do this way. And this one, of course, is a summation of M Cm. According to what we have learned, this will be Cm and A M M and the percent Mx, right? Okay, so let me change the order slightly. Make this the summation of percent M and A M M Cm. Do the summation of M, okay, and then do a summation of M. So you can see that this one is just the new coefficients, right? So this is equals to summation of M Cm prime percent Mx. With this Cm prime just equals to A M M Cm. Do the summation of M. So look at this one. This is just exactly the same form as the matrix product, right? So if you write down that in the matrix form, so this percent just equals to say C1, C2, okay? And then after the transformation, you got a psi that equals to psi prime. Okay, and this psi prime equals to C1 prime, C2 prime. It's nothing but just matrix A times C1, C2, Cm, right? So this way, as long as you know how the basis transform, okay, you know this matrix. As long as you know this matrix and you know the transformation of any state, okay, it's just the product of matrices, okay. So that is, you know, kind of interesting, right? And now we also have, let's say, okay. Another way to write down the Dirac rotation of an operator, right? The simplest way is that, for example, you can write down an operator like this one. Let's look at what is this one. Okay, so you can see that this one, all acting on psi. What will be this result? This equals to m and the psi. Okay, so now you can take this one as an inner product. Okay, and this one is the new state. So basically, the effect is that the operation, this operation that you first of all check the probability of m in the state psi, right? And then transfer it into the state n, okay? So if the probability is 0, of course, the state is 0. And if the state is m, okay, then it's m, okay? So this one, of course, for example, you can act in this one on just one of the state, say k. So that way equals to m and the k. So this, of course, will equals to delta m k and m, right? So only when the state is in m, and then the state will be transferred into m, right? Okay, so that is just one state. And for any of this one, so you can also have a more general case. That equal to summation of a, m, and m. You do a summation of all of this one. And let's see what will happen, okay? So look at let's check the matrix form of this one. Okay, this one, of course, can be also written as a summation of KL and A, KL, K, and L, right? And let's look at the matrix form. So look at the A, M, M. That, of course, equals to K, M, and A, and M. That equals to summation of K, L, M, and K, and L, and M. Now you have two inner products. Okay? So this is the inner product. And now you can take this one. This is a C number, this is also C number, but the first one is just the second one is just another data function. So the result is nothing, sorry, times AKL. So the result is nothing but just AMM. Okay. So basically, so this means if we have an operator, so if you have an operator A has a matrix element AMM, that equals to psi M A psi M and equals to MAM. And then the Dirac notation of A can be written as just A equals to summation of M and M, A, M, and M and M. Okay, so this gives us a Dirac rotation of the operator. Okay, and this actually will be and very convenient. Okay. For the calculations. Okay. Once you get familiar with these notations. Okay. Right. So let me give you a small summary of the syntax of Dirac notations. Okay. Okay, so state is very simple. It's psi m or summation of m c m m, so on and so forth. So this one is the Q number. Okay, Q number is kind of like a quantum number. You can have a conjugate. Okay, so psi, okay, or m, or summation of m and m c m complex conjugate. Okay, so this one actually can be written as psi takes image conjugate. If we compare the matrices, right? So you know that this one is just m and the complex conjugate, and this one is the summation of m, cm, and m, and take the image conjugate, right? Okay. Right. So on and so forth. So this one are also Q number. Okay. But this is type. Let's say type Kate. This is broad Kate, a broad type. So you have two kinds of Q numbers, okay? And you can also have the inner product. Right, for example, psi phi or mm, okay, or psi summation of m, cm, m, okay, and so on and so forth. And this one actually can be written as phi psi, take the complex conjugate, or m and m, take the complex conjugate, or summation of m, cm, sorry, m, complex conjugate, and psi, and take the complex conjugate, right? So this one is the C number. Or if you want to use a matrix form, this matrix, this is m times 1 matrix. This is n times 1 times m matrix. Okay. And this one is a 1 times 1 matrix. But it can also be understood as I, that's n times m matrix, times C, okay, a constant. So you have different ways to understand it. This one can be either as a 1 times 1 matrix, that's a C number, or just a unit matrix that's commutable with everything, right? So a good thing for this one is that this one commute with all, okay? So that means you can move this one freely, okay? And then another thing is the operator. Right, you can have psi phi, you can have m, you can have summation of m, a, m, m, and m, okay? So if you take the image conjugate, this will be this one. The image conjugate of this one gives another one, right? So this one, m and m, image conjugate. Okay, and so on and so forth. So this will be, if it's also Q number. It's a Kate broad type. Okay. In terms of matrix, it's n times m matrix. Okay. Right. So you can see that you can have 1, 2, 3 types of Q numbers, and then you have the C number right here. Okay. Of course, you can also have just a complex, any complex number. You know, it's also a C number. Okay. So you have these four kinds of quantities. Okay. And now the rule is to form the formula that so rule 1, summation must be between same type. But for example, you cannot say that in physics we know that you cannot say that 1 kg plus 2 meter. This is not allowed, right? Because this one is mass, this one is length. There are different types of quantities, so you cannot do the summation. Okay. And similarly, you cannot say something like this one. This one is not allowed. Oh, sorry. This is allowed. This one is not allowed. Because this is cat, this is bra. But this is n times m matrix. This is 1 times m matrix. You cannot do the summation of these two different kinds of matrices, right? So this kind of summation is not allowed. Okay. You cannot do something like this one, pi over 4 plus percent. This is not allowed because the first one is a C number, the second one is a state. That's not allowed, okay? Right? You cannot do something like this one, say percent and phi plus percent. This one is not allowed because this one is the operator. This one is a state, right? Okay, what are allowed is that right 1 kg plus 2, 2 ton. Okay, this is okay. Even though they have different units. Okay, but kg is the mass, tons is also mass, so you can do the summation. Okay, so you can do this one percent plus e to I phi and m. Okay, this is okay. You can have this one percent and phi plus phi and percent. Okay, this is operator plus operator. That's okay. You can have percent plus phi and e to minus I pi over 2. This is also okay. Okay. You can also have something like this one. It's also okay. Like a percent phi plus 1. This is also okay, even though this is C number. This is, in this case, you take this 1 just equals to 1, 1, 1. It's a unit matrix. Okay, so it's also not okay. So basically, the rule is that when you do a summation, it must be of the same type. Okay. And rule 2. In the product, order is important. Okay. You cannot change them, and so all this one must have so the contraction rule of a matrix product. For example, okay, look at this one. This is percent. This is phi, right? Okay, so this is percent, this is phi. You know that this is n times 1 matrix. This is 1 times n matrix. So this is okay. See that this has 1 indices. Index just has 1 choice. This has also 1 value. So you can do the summation of this one. So this result will give you n times m matrix. Okay, you can times the C number right here. For example, ei pi over 3. That's okay because C number is you can take this as either unit matrix or just a C number that can be moved anywhere. And now here, remember this is m. This must be n times something, right? So it's either a broad state, say m. Okay, and inside this one you can times another. Okay, so 1 plus I, for example, this is not the same number. That's okay. And now this is n times 1, right? You take this one as n times m. That's okay. And now this one is 1 times 1 because this is 1. This must be taken on the as 1 times 1. So on the right hand side, if you want to continue this product, so what you have must be, certain kind of branch state, because you must have n times 1 times m something, right? So you can continue this one. So you can say that every of this one, so this is just a matrix product. So the first one is n times 1, and then the next one must be 1 times something, right? It cannot be n times something. So for example, this one, okay. So this one is not allowed because this is n times 1. This is 1 times m, okay. But this one is also 1 times m. So you cannot have a matrix product like this one, okay. So this one is not a valid formula, okay. That's one thing, okay. So another thing is that if you have, for example, psi, phi, chi, eta, okay, and now this one is 1 times 1, it's a C number, so it can be moved anywhere to here or to here if you want. So that means equals to psi and chi. Okay, so this is just a C number, and then times phi and eta. So you got a n times m matrix, and then times the constant, right? It's also allowed. So that's the second rule, okay? So once you know this one, and then you can actually do a lot of things, to play, okay? Let me give you one example. Okay. Let's look at the completeness. You know that for complete, we said that any static per se can be written as a summation of m and cm and m, right? With cm just equals to m per se. And now we can do this one very easily. Okay. We just say the completeness just means the summation of this m, do the summation of all the bases, just equal to 1. This is very easy, right? So if you look at the matrix element of this one, because if we define this one as a matrix, if we define like a matrix A equal to summation of m and m and m, you can see that this m and a and m will equals to delta m m, right? So that means this matrix is just a unit of 1, right? And now you can very easily write down this one as psi just equals to 1 times psi, right? Of course, right? So that equals the summation of m and m and psi, right? Okay. Okay. And now this is a C number. So that equals the summation of m and m psi and the summation of m. So we compare this one, I call this one Cm. Right. So it's just everything is consistent, right? So this gives us an example of how this formula, how this formalism works. Okay. All right. I cannot get you familiar with all of these notations in just 10 minutes or 20 minutes of introduction of this notation. But we will have more examples later. So when you use it more and more, you're going to know this more and more, okay? And then there's a special, okay? Right, we know that for any operator, that can be written as A, M, M, and M, dimension of M and M, right? So the matrix is just A, okay? And we know that in matrix, we have something called an emission matrix. That is basically, we say that this one just equal to this, or equivalently, we say that AM equals to AMM complex conjugate, right? So we say that if A is emission, then we say that this operator is an emission operator. That's definition. Okay. The physical meaning. Okay. So this actually means for any state A and the percent is a real number. This is important, okay? And because if we do the measurement of physical quantity, you know that the expansion value is just given by this one. So this must be a real number, right? So that means we probably want to require all the physical quantities to be real, to be emission operators, okay? So this actually is also an alternative definition, okay? See homework problem, okay? So you are asked to prove that emission operator actually is equivalent. The definition, the previous definition is equivalent to this one, okay? And also you can say that for any state per psi and A of phi, so this must equals to phi and A and per psi complex conjugate. And in terms of the integration, we say that equals to so not this one acting on this, remember. So in this one, this I acting on phi, but on this one, this A acting on per psi, okay. So this is important to the left state. Okay. So you can see that this operator A can be acting on this one or that one, okay. But you need to take the complex conjugate. And if these two are the same, and then we say that this one is emission, okay. So this one is equivalent to this one, is equivalent to this one, is equivalent to this one, and is equivalent to this one, okay. All these four definitions are equivalent. And the physical meaning that we want to have an operator that has real expansion values, okay. Right? And you know that the emission matrix, okay, if it's n times n dimensional, has n eigenvectors with m real eigenvalues. Okay, this is the linear algebra. Okay. So what means this one? So that means if I have A equals to A DAC, and then so there are m, so m per se m with A acting per se m equals to am per se m, and am is a real number. Okay. So this means equivalently, so you have an operator A, there are n states, there is A, M, and M, with AM is a real number, okay? Right, so that is an important thing of this emission operator. Okay, right. So then, with this, all these definitions, this introduction of mathematics, so now we can say that postulate two, all physical quantities are emission operator on a Hilbert space. Okay, that's it. So this is the the posterior tube. Okay. Let's show some examples. X, right? You know that percent, any percent X acting on this percent, sorry, phi. Okay, so this one just equals to and this one obviously equals to so you must have this X is emission. Okay, that's easy, right? And secondly, momentum. So this one can be written as h bar over I d over dx. Okay, so you can see that the emission operator is not necessary real. Okay, so you can say this is not a real operator. This one is actually is imaginary. But now we can prove that if you have percent star x h bar of I d over dx and phi x and dx. And now we can use the integration by part. This can be written as percent x times h bar of I and phi x. Do this one, right? And then minus, you know, h bar of I d over dx and the percent star x. Okay, and the phi x and dx. Okay. Now this is important. This one equal to 0 because of so this is 0. That's called a well-behaved wave functions, right? For example, it must be normalizable, and then this wave function must vanish at the infinite. And the second term, and then obviously it's just phi x and h bar over I d over dx percent x dx, and then you take the complex conjugate. Right. So this one is also proved. Right. So that is the momentum operator. Okay. Right. So you can also prove that say I leave this as an exercise. For example, the kinetic energy, that's the momentum squared. That equals to minus, you know, d squared over dx squared, h bar squared over 2m. Okay. Or you can of course have this one equals to vx, right? You can also have, for example, Lx equals to y pz minus z and py. Okay, and Ly, Lz, and L squared. Okay, all of this one, they are emission operators. Okay, so this one equals to this one equals to this one, and so on and so forth. Okay, so I leave this one for you to, you know, to do some exercise. But also you can just, if you don't want to do this one, you can just believe it. Okay, so all physical quantities must be emission operators. Okay, all right. So let's take a break and see if you have questions. Right, so you have heard a number of times something called diagonalization. Okay, so what does this mean? So in mathematics, linear algebra actually is very simple. Suppose you have an operator A, that's admission. Okay, and then we know that all these matrices would have, suppose it's n times m, admission matrix. Okay, and then there will be n eigenstates. Okay, so if I want to be more specific, I say that A11, A12, A21, A22. This is the matrix, right? And times this, say, let's say, let me call this one U1M, U2M, U3M. And of course, there's UMM. So I call this one psi M, okay? Okay, so this one is just the matrix A. That will, of course, equals to U1M, U2M, and UN, little m, times AM, right? And there will be n such vectors. Okay. So if I put all of them together, so you can see that I can put all of this one. So I can put A11, A12, A21, A22. I can put this. This is the first column. That's U11, U21, U31, and UN1, and U12, U22, U32, UM2, and this is U1M, and this is UMM. So you can see that this one is psi 1, this one is psi 2, and this one is psi m. Okay, and this A matrix acting on the first one will just give you the first column U11, U21, and UN1 times A1, right? Okay. So, and then the second one is U12, U22, UN2, and then times A2. So it can be written like this form. So you can check. So A times the first column equal to A1 times this column, and A2 times this column, this psi m, psi 2, sorry, this is psi 1, and then this is psi m. So the matrix times the first column will equals to A1 times the first column, and matrix times the second column will equals to A2 times the second column. So this one can be written into this matrix product, and this one is we call this one lambda. Is n times m diagonal matrix. Okay. Right. So let me call this one the matrix U, and this one is also matrix U, right? And this one is matrix lambda. So this one becomes A times U equals to U times lambda. Okay, lambda is diagonal. But now, because this U, this basic states, we have psi m dagger and psi m equals to delta mm. This is also normal, right? So that means, so this column and this different columns are orthogonal. The first column are the and each column is normalized. So this basically means U DAG times U equals to 1, 1, 1, 1, 0, 0, just equal to 1. Okay. So that means we can write down this U DAG A and the U equals to lambda. So let's say that so this U DAG equals to U minus 1. So it's called a unitary matrix. Okay. And the lambda equals to A1, A2, AM 0, 0 is a real diagonal matrix. So that's why this is called a diagonalization in matrix. And then in quantum mechanics, you know that suppose you have a state, you have A acting percent M equals to AM percent M, right? And correspondingly, you're going to have a state percent M equals to AM percent M. With this percent M just equals to summation, you know, M U, sorry, M and J, U, J, M, okay. Right. So that's what we say that if we find in other words, we say that the U DAG times A and the U will equals to lambda. That's nothing but just a summation of AM and percent M and the percent M. Okay. So this is called so we call this one diagonalization. Sorry. This is the diagonal matrix. So that means A equals to summation of AM and percent M and percent M and M. Okay. So in this basis, this A is diagonal. Okay. Right. So that's called a diagonalization of an emission operator. Okay. So basically, if you find all the eigenstates of an emission operators, we say that we have diagonal this one. Okay. So that is what we have. For example, if we have a Hamiltonian, like remember this one is P squared over 2M plus M omega squared over 2 times X squared, right? So this is the operator. But this one can be written as a summation of EM and M and M for M equal to 0 to infinite and EM equals to M plus 1 over 2 H bar omega, right? So in the matrix form, this H just equals to H bar omega, sorry. H bar omega, 1 over 2, 3 over 2, 5 over 2. Okay, so this is an infinite dimensional matrix. It's diagonalized. Okay, and this Hamiltonian now can be written as this diagonal form. Okay, so whenever you can write down Hamiltonian like this form or any operator like this form, you say that we have diagonal this one, right? So that is it's called a diagonalization of the matrix. Okay, right. So there are some other things that that's written in the lecture notes. Okay, so I will skip that one. So leave you to read. Okay, so that's we have for this emission operators. Okay, quite a lot. And what's interesting is that we have this very nice Dirac rotations. Okay. And now we say that we have a physical quantity A, okay? So it's emission, right? For example, momentum, position, L, L squared Hamiltonian. Okay. So on and so forth. These are all physical quantities. And if A is measured, so what do we get? Okay. So the postulate 3 tells that, so if psi equals to summation of m, cm, and m with this a act m equals to am m. So that means these are the eigenstates of this operator. So all the psi can be expanded by this eigenstates of a. Okay, and then the output is randomly. Okay, so this is something surely unusual in physics. Okay, am and corresponding m. So the output is this one, the state after measurement. Okay. This is the measurement result. Okay. Right, and it's randomly, so you for many identical copies of psi, okay, on which the measurement is done. Okay, the probability will just equals to cm modulus squared and cm. Okay, of course, if the state is normalized, or Pm just equals to if it's not normalized. Okay, right. So that is the statement. We have discussed quite some results of this one. Okay, right. And then the importance is that so you have expectation value. Okay. So that means, first of all, you need many copies, okay, of psi, okay. And then the expectation value of this A, of course, is just summation of m, pm, am, right? So that's equals to summation of m, cn conjugate times cm times am, right? Okay. So what is cn? So psi equals to summation of m, cm, m, right? So cm equals to nothing but m psi, right? So cm compass conjugate just equals to psi m, right? So now let's do some exercise of the Dirac rotations, okay? So it's this, okay? You gotta okay. All right, let me copy this one again, okay? A equals to summation of m psi m and a, sorry, and psi and am. Okay, so this one depends on n, this one depends on n, this one depends on, but this one is nothing, it's not depends on n, okay? So now let me remember this is a 1 times m matrix. This is n times 1 matrix. This is 1 times m matrix. This is n times 1 matrix. This is 1 times 1 or n times n. It's up to you, right? And now you can move this psi right here, okay? It's still correct, right? Because this one is a C number, so it can be moved freely. And all of this one contains M. Okay. But you can also write it like this way. AM is free. You can also write it this way, right? This is also correct. Because AM is just a C number, so it can be moved freely. And the summation now is only on M, so you can read it inside this one. Okay. But what is this? Because A acting on M equals to AM, right? It's eigenstate. Okay. So this can be also written as A acting on M and M. And per se, right? Okay, great. And this one does not depend on N now, right? It can be moved outside. So this equals to per se A summation of M and M and per se. Okay, what's this one? So summation of M and M. Remember, this is a direct rotation, right? So in the matrix form, it's just 1, 1, 1, 1, 0, 0. So that means this one just equal to 1, right? So that means this one is not just per se and A and per se. So we got a beautiful result, okay, with all of this mathematics. Okay, let me just write down this beautiful result right here. A equals to per se and A and per se. So the result that so the way to measure the expression value of this A mathematically is just like you apply this operator on the state, and they see how much is left. So that makes a great sense, right? So you just see how much is the left after this operation, okay, in the original state. If you leave this one a lot, that means you got a state that's you got a large amplitude, right? Otherwise, you got a small amplitude, okay? You got 0, for example. Okay. So it becomes the overlap between the states before and after the operation, okay, right? So that gives us the expression value, okay? And similarly, you can calculate the variance. Okay. So this one actually equals to A squared minus A squared. Okay. The result is actually per se A squared and the per se minus per se and A per se A squared. Okay. So of course this is very easy to prove. Okay. So this one equals to a summation of again Cm, okay, square complex conjugate Cm. Now this is M squared, right? I do a summation of M. Okay. So I leave this one as access for you. Okay. The result is simply, per se and A per se the square. Okay. All right. And the important thing that so in quantum mechanics, okay, you can choose an eigenstate of A, okay, and then you can say that the per se M and M is nothing but just AM, right? And what is A squared? And this one, of course, is just M and A and A and M, right? So this just equals to M, A, and AM and M, right? So it's nothing but just N squared, right? So that means the variance is 0, okay? But the point is that if percent is not an eigenstate of A, okay, and then you can have that A in general is not 0, right? So this is a quantum fluctuation. Okay, and the point is that so if you have two operators A and the B, they commute. So when I say that you can have simultaneous eigenstates. Okay, so that means you can have a state M, so that A acting on this one equals to A, M, and M, and B acting on this one, N equals to BM and AM. Sorry, M. So this one immediately tells us both delta A equal to 0 and the delta B, the variance also 0. So this is possible, right? Okay. But if the two does not commute, or if A and B do not commute, okay. So in general, you can say that so this one equals 0, and then probably you have this one is not 0, right? Okay, or this one equals to 0. That means the eigenstate of, so this means the eigenstate of A. Right. But it's not the eigenstate of B. If the eigenstate of B is not eigenstate of A, right? Okay. So you cannot choose. There's no simultaneous eigenstates, right? So in this case, so you can have many copies of percent, say for example, and they can use NA copies to measure A, and MB copies to measure B. So we can prove that the variance of this one, delta A and delta B, that satisfies the condition that is actually at least is greater or equal to 1/2. Okay. The commutator between the two, and then squared. Okay, so for the proof, see the notes, okay. And in particular, for delta X and delta P, you know that the commutator between X and P is just IH bar, right? So that equals to, okay, sorry, that's a square. Okay, or you have delta X, delta P is greater or equal to H bar over 2, okay. So this is the Heisenberg uncertainty principle, okay. And the important thing is already given right here. You can see that here I say that I actually have different copies. On these copies, you just measure A. On that copy, you just measure B. So there's no interference between the two measurements, okay. So this is not, it's not because of measurement of A disturbed the state. Okay. So I know that in many textbooks, unfortunately, they said that the reason that you can have this uncertainty is because if you measure A and then you're going to disturb the state, so that the B cannot be measured more precisely, okay. This is not true, okay. You can actually have many copies and use these copies to measure A and those copies to measure B. They don't actually, interfere with each other. It's the intrinsic It is the intrinsic property of quantum states, okay? Right, it's just like a Fourier transform. If I have wave packet, if I have the position of this wave packet well defined, and then the momentum of that, the wave vector of that one is not well defined, okay? Right? So like the position and the wave vector of wave packet. You don't need to do any disturbance to the wave packet. And this wave packet intrinsically cannot have both the position and the wave vector well defined, okay? So they must satisfy this uncertainty principle, okay? It's an intrinsic property of the quantum state. So that's one thing I particularly want to emphasize, okay? Right? Okay, so that's the postulate 3. And now we can consider the postulate 4. That's about the quantum evolution. Right? Of course, we have the time-dependent Schrödinger equation. So that is, for example, I h bar partial t psi xt equals to the Hamiltonian, right, of x and the p acting on psi xt, right? So this is the time-independent Schrödinger equation, okay? So in Dirac rotation, we say that we have this one. Okay. Right, so that's the evolution. If we have the time-independent Schrödinger equation, we solve the problems, right? Suppose we have done this one. Okay. And then, if we have psi 0 equal to summation of m, cm, and m, and then we have to know that the psi t actually can be easily obtained by the linear nature of these operators, right? That equals to summation of m, cm e to minus I e m t over h bar and m, right? So this gives us the solution, okay? Okay. So that's the one thing we have learned, okay? But now I want to introduce another important thing, okay? So I would like to look at the evolution of measurement. Okay, so basically, I'm interested in this one. So what does this mean? So we have many copies, okay, psi, and then evolve by t to psi t, okay, and then measure a, okay, and then for each t, you got this a, right? That of course equals to psi t and a psi t, right? Okay, and then as a function, that means you do these experiments for different t. Okay, so do experiments for different t. Okay, you're going to have different a, right? So the question is, what is this one? And this actually will give us a very nice and beautiful result. So this is something that I cannot resist to tell you. Okay. And this one, of course, if you write down, it's actually pretty simple. d over dt. It's just psi t and a and psi t, right? But very simple differential equations, you know that this will have two terms. One is it's just d over dt psi t and a psi. So you take this as this is a 1 times a matrix This is n times m matrix. This is m times 1 matrix, right? But you can also have another term per side t, and a d over dt, and per side t. And this one, of course, can be obtained by the time-dependent Schrodinger equation, right? But then the question is, how about this term? Right. And this one actually is given by the conjugate, okay, of the Schrodinger equation, okay. So let me write down first of all, you know that if you have I h bar partial t per psi xt, that equals to x Hamiltonian xp and per psi xt, right? So this one equals to minus h bar squared over 2m, so partial squared partial x squared, and then plus vx per psi xt, right? Okay, so that's the Schrodinger equation. But now we can look at the conjugate of the Schrodinger equation. So you take the conjugate, so basically, you just take this one, the conjugate, and this will be minus I, right? And this one will be the complex conjugate. That's the complex conjugate, right? So you got a partial t per psi complex conjugate xt just equals to, and then I over h bar minus this one, right? Okay. So that is the also Schrodinger equation, but it's a Hermitian conjugate. In another way, in Dirac rotation, it's probably even simpler. I will use two ways to do this one so that you can get more familiar with. But we know that the I h bar partial t per psi equals to h per psi, right? Let me do the Hermitian conjugate. Okay. I know that if we do the Hermitian conjugate, so all the coefficients have changed to the complex conjugate. So it's minus I h bar partial t. And now this one become the Hermitian conjugate. And this one will become the Hermitian conjugate. And this one will be also the Hermitian conjugate. But Hamiltonian is Hermitian. So this one equals to per psi and h. So let me check. So this one is the n times 1 matrix. But this is 1 times m. So if you do the Hermitian conjugate, it will be n times 1. And this one is n times m. This one is the n times 1, right? So do the Hermitian conjugate, this will be, sorry, this is n times 1, sorry. And this is 1 times m. Okay, so this will be 1 times m. This will be n times m. This is 1 times m. This is n times m. So everything looks fine, right? So that is another way to do this one. So use the Dirac rotation, actually. If you're familiar with it, you don't need to check all this time. So if the matrix is correct. But you know, if in the beginning, you probably want to do this kind of a check, okay? Right? So make all the coefficients to be complex conjugate and change the bra to cat to bra, okay? And then you can check all this one to be, it's fine, okay? Right, so that's the conjugate. And now let's look at the expansion value, okay? So we have two terms. So the first one is very simple. It's per psi t and a d over dt per psi t, right? Okay. So this one, of course, is very simple. It's just per psi t and a. So what's this one? What's this one? It's just minus I h bar times a, right? Times Hamiltonian. Sorry, over h bar. Okay. Right. everything is correct, right? And then you have another term. That's d over dt per psi t. And then a and the per psi t. So you just apply the emission conjugate of this one. So that will be per psi t. And then h. Now this is I over h bar. And a and the per psi t. Okay. And look at this one. You can combine these two. This just equals to I h bar per psi t and Hamiltonian. And it's just a commutator of this one. So you got an important result. Okay. So this is the derivation in the drag rotation, okay? Let me do this one, okay? Let me do this one again. In wave functions. If you don't believe me, right? Okay. Let's look at this one, d over dt and a, okay? So this one, of course, equals to d over dt per psi xt and a per psi xt, right? dx. And this one, you have two terms. One is per psi compass conjugate and a and per psi, sorry, d over dt per psi xt, right? And dx. Okay, and you have another term, d over dt compass conjugate xt. Okay, and a per psi xt dx. The first leg is very simple, just the Schrodinger equation, right? So just apply the Schrodinger equation. So that equals to this one and a, and this one is nothing but just minus I over h bar and Hamiltonian acting on this per psi xt, right? And dx. Okay, so you got this term, right? And then you plus another term. The other term will be slightly, so it will equals to I minus I over h bar h acting on per psi xt, and then take its compass conjugate, right? And this is a and the xt, okay, dx. Okay, now take this one as phi. Right. Remember, for emission operator, you have for psi x o phi dx equals to, you know, o psi compass conjugate and phi dx. Right. So this is for the emission operator O, okay. So remember, H is the emission operator. So that means we can apply this one to this. So the result is simply that's the first term, right? And then you have another term. So now I can take this one just as the emission operator. So I can just move this one out and make this one act on this. So the result is simply I h bar act on phi, and phi is nothing but a per psi xt. Okay. So now you can see that this one is nothing but just equals to okay. Right, so we prove this one. for the evolution, right? Okay, so that's the formula, important formula we have for, we have two proofs, okay? This way or this way, okay? They both prove it, right? Okay. And now from this one, we can actually have a very simple application. Remember in the previous we said that the Aaron first theorem. Okay. Now this is not optional anymore, right? Because it's very simple. Okay. So let's look at the x. Suppose you have a Hamiltonian that equals to p squared over 2m plus vx. And you know that now we can look at the evolution. Okay, and this will equals to I h bar, the Hamiltonian, and x, and take the average. That equals to I h bar p squared over 2m and x. This is nothing but just p over m, right? And then d over dt, the momentum, that's I h bar, Hamiltonian commutator with the momentum. That equals to I h bar, okay, vx, and the momentum operator. So we have done this one before. This one is nothing but just minus partial x. Sorry. Right. So if we compare this one, classical mechanics, I remember partial xv is just a force, right? And p over m is just a velocity, right? So this looks like a very much like the classical mechanics. Actually, in the classical mechanics, you have d over dt x just equals to x and the Hamiltonian, the Poisson bracket, and d over dt momentum that equals the momentum quantity and the Hamiltonian, and the Poisson bracket. Okay, so it looks very much similar to classical mechanics, right? But they're actually not exactly the same. Okay. Okay. A lot of the same. Okay. Right. First of all, expectation value is on many shots of measurement. Okay, in quantum mechanics, this is one thing. And secondly, so V prime x averaged does not equal to V prime of the average x. For example, if Vx equals to a over 4 x force power, and then V prime x will equals to a times x power 3. And the average of this V prime just equals to a x cubic. And this one does not equal to a x cubic because of quantum fluctuation, right? Okay. So that is an important difference between this quantum evolution and the classical evolution, okay? But of course, there's a special case. The special case is that Vx just equals to kx squared over 2. In this case, V prime just equals to kx. So average of V prime x just equals to V prime x of average, right? Because both of them just equals to k and x. So in this case, you got that d over dt x just equals to p average over m. D over dt momentum average just equals to minus k x. Looks like the same as, so if we plot this one in the phase space, so this average of x, this average of p, so the motion is just, okay, right, it's the same as classical mechanics. But again, because of this one, well, not really, right? Because it is just the average. It's not because in each measurement actually it will give you different results. Okay, there will be still fluctuation. Okay, so anyway, there's still a fundamental difference between this quantum mechanics and the classical mechanics. Okay, so anyway, so you can see that enough using this formula. So it's this iron force theorem now is easily proved. Okay, and before it takes a little bit of efforts, but right now using the formalism looks like very simple. Okay, and also it looks. This one also disclose, okay? This one disclose a fundamental connection, between quantum mechanics and classical mechanics, right? Remember, in the classical mechanics, we said d over dta equals to an a and Hamiltonian, the Poisson bracket. So that means if we make this kind of change, okay? So you have the classical mechanics change to the quantum mechanics. Okay, this one was discovered by Dirac in 1925. So that's an extremely beautiful result. Okay, right. So this is a very quick and brief introduction of the formalism of quantum mechanics. Okay, I don't think that it's a good way to learn this formalism just by memorize this one. The best way to learn this one is just to apply, to use these rules more and more, so that you get more and more familiar with those symbols, this grammar syntax. Okay, and then once you got a good grasp of this one, and everything will be just trivial. Okay, and then you can focus on the physics. Okay. All right, so we're going to stop right here. We're going to have more application of this formalism in the spin half problem. Okay, and